Deep neural networks for the estimation of masonry structures failures under Rockfalls. Welcome to Journal Club. The latest academic research, explained in plain English. Today we're looking at this paper from MDPI's Journal of Geosciences. It's authored by Mavruli, et al., from the University of West Attica in Greece, and is published open access under a CC BY license. Let's start by translating the title into more accessible language. When you read this title, you can understand it to mean in very simple terms that this paper is about using advanced computer programs to predict when rocks might fall on walls and cause damage. Let's expand on that a little. In this paper, the authors used a type of artificial intelligence called deep neural networks to predict when masonry structures, like buildings or walls, might break or fall apart because of rocks falling on them. Now we understand the title, which is a good start, but before we can break down the full paper, we'll need to catch up on some terminology, jargon, background information and context. Specifically, there are some key concepts you'll need to be familiar with. Let's define them now. Rockfall. The movement of rocks or large boulders down a slope or steep surface due to gravity or other forces. Masonry structures. Structures made of brick, stone, or similar materials that have been bound together with mortar. Failures. Instances where a structure is unable to maintain its normally expected performance or serviceability under specific loading or environmental conditions. Estimation. The process of making an educated guess or approximate calculation about a value or quantity. Deep neural networks. A type of machine learning model composed of stacked layers of artificial neuron that are able to learn and make predictions based on complex patterns in large datasets. Empirical data, information gathered through observation or experimentation in the real world, often used to inform or validate scientific or engineering models. Numerical methods, mathematical algorithms and techniques used to approximate solutions to complex equations or models. Artificial intelligence, AI, a broad field of computer science and engineering that focuses on developing machines or software programs that can perform tasks that normally require human-like intelligence, such as learning, problem-solving, and decision-making. Finite element method, FEM, a numerical technique used to solve complex engineering problems by dividing a physical system into smaller, simpler elements and analyzing the behavior of each element individually. Damage index, DI, a metric used to quantify the amount or severity of damage to a structure, often expressed as a percentage of the total surface area that has been affected. Now that we understand the title and key concepts, we're ready to dive in and break down this paper. In this presentation, we're going to attempt to answer 5 questions. 1. What were the researchers trying to figure out? Or more specifically, what was their hypothesis? 2. How did they conduct their experiment? That is, how did they test their hypothesis? 3. What were the results of the experiment? 4. What conclusions did the authors draw from those results? And lastly, 5. Why does this research matter? Why should you care? 1. What were the researchers trying to figure out? The researchers hypothesized that artificial intelligence methods can be used to accurately estimate the expected damage of masonry walls when subjected to rockfall impacts, providing a simpler tool for assessing rockfall vulnerability of buildings. 2. How did they conduct their experiment? The researchers developed a large analytical database for estimating rockfall damage to masonry structures, consisting of 672 datasets with 5 parameters each. They analyzed statistical indices and Pearson correlation coefficients to determine the degree of correlation between the input parameters, rock volume, rock velocity, wall thickness, and masonry tensile strength, and the output parameter, damage index. They then used artificial neural networks, ANNs, to model the relationship between the input and output parameters, with a conventional feed-forward ANN architecture that includes input and output layers and one or more hidden layers. To assess the effectiveness and reliability of the predictive models, the researchers used performance indices such as Pearson's correlation factor and the A10 index. 3. What were the results? The researchers trained and developed various artificial neural network (ANN) models to predict rockfall failure of masonry walls and identified the optimum ANN model, the ANN LM4211 model. This model achieved almost ideal performance results. Using this model, the researchers developed a closed-form equation that can be used to estimate the damage index of masonry structures under rockfalls as a function of input parameters, such as rock volume and rock velocity. The researchers also provided a series of charts to help estimate the vulnerability values for use in rockfall risk equations. Wall thickness and masonry tensile strength were identified as important parameters for predicting the damage index. 4. What conclusions did the authors draw from their results? The best model was found to be the ANN LM4211 model, and the wall width and masonry tensile strength were found to have a significant impact on the resulting damage. The authors suggest that neglecting these factors could lead to unreliable results during risk analysis. 5. Why does this research matter? This paper is important as it presents an alternative method for assessing the vulnerability of masonry walls to rockfall impacts. The use of artificial intelligence (AI) methods can provide an accurate and reliable way of predicting the expected damage caused by potential rockfall scenarios. This can be helpful in risk analysis and management, as it provides insights into the impact of rockfall on buildings and can inform decision-making on protective measures. Additionally, the paper highlights the importance of including factors such as wall width and masonry tensile strength in risk analysis in order to obtain reliable results. We hope you've enjoyed this Journal Club presentation of deep neural networks for the estimation of masonry structures failures under rockfalls. If you'd like to read the full paper yourself, which we encourage you to do, you can find it at DOI 10.3390/Geosciences 13060156.